Hello, chemistry students. Today we are going to talk about a calculation that you can use in the laboratory. And we have done a similar calculation to this in Chapter 2, and it was called percent error. Okay? And in percent error, we had a couple of things. We had an experimental value. So I'm trying to refresh your memory here. Experimental value, and this value was what the actual is not a good word, what the real value was. So if you looked up density in a book, this was the real value, and if you were testing the density, the actual value is what you got when you did the lab. So the actual value is what you got. Okay, and what we're doing today, this percent yield, is very similar. This except is measuring the percent of your error that you did. So you recover something, you measure the density of something, and you compare it to what you might read in a book, okay, or you might see me write on the board or whatever, and you can calculate doing multiple trials to see how close you got to the experimental value. Okay. Now in percent yield, it's a little different because the theoretical yield, it is actually something that we can calculate using stiochiometry. That is the real value, but it is calculated. Okay, so we can use this calculation to figure out what the theoretical yield should be, and then when we do the lab, we get an actual yield that we can compare back to the theoretical yield. Okay, so the actual calculation of percent yield really isn't that difficult, but what is a little more challenging is this calculation of the theoretical yield. Instead of just giving it to you like we did in Chapter 2, now you're going to have to calculate it using stiochiometry. Okay, so I'm first going to do a problem of how to calculate theoretical yield. Okay, so this is on page 374 in your book, and I'm just going to do the example problem for you. So they give us an equation. It says calcium carbonate. This is the substance that you use to make your sterno in the s'mores lab. Okay. And when we break that down, we get calcium oxide, which is a solid, and CO2 gas. Okay, so if you were to heat this, this takes heat. If you were to heat this, it would break down into these two things. Now this is already balanced for us. We have one calcium, and one carbon, and 3 oxygens. So we don't need to do any balancing, which is nice. But now we need to calculate what the theoretical yield is of, it has to be a product. So since we would have to trap this gas and it's a little bit harder to measure, we can calculate this pretty easily because it's solid, so we can weigh it out at the end. Okay. So what we're going to say is we're wanting to find out what the theoretical yield is of this, okay, since it's a product, if we use a given number for the product. So I could go into the lab, we could get out that big container, we could weigh out this, and let's just say in this case we had 24.8 grams of this calcium carbonate. Okay, and we want to know what our theoretical yield is. Okay, how much we're going to produce over here. So this is what we've been doing for the last two sections with stoichiometry. We've been able to go from reactant to a product or vice versa using this mole ratio. Okay, mole ratios are going to be used in every stoichiometric problem. Okay, if it's stoichiometry because of the mole ratio. If you're not using a mole ratio on a stoichiometry problem, you're not doing it right. Okay, so those mole ratios are really important. So obviously, if we're going from here to here, the mole ratio that we're going to be using is going to be 1 mole of CaO over 1 mole of CaO3. Okay, so since we're going from here to here, we know that already. Okay, So let's go ahead and write our given number out. So we got 24.8 grams of CaCO3. Make sure you're labeling. Okay. Put grams on bottom of CaCO3. The book tells us that it's around 100.01 grams, and that's in 1 mole of CaCO3. Now we're going to use a mole ratio. Let me erase this line here. This thing's in my way. So we need to use a mole ratio. So 1 mole, or the mole of CaCO3 goes on bottom, so it cancels out. So we have these grams cancel out, these grams cancel out. Now we have mole and mole cancel out. So now 1 mole of CaCO. Now we're at least a CaO, and now we're just trying to find what it is in grams. So now we're going to put 1 mole of CaO on bottom. If you calculate the molar mass of that using the periodic table, we would get 56.1 grams of CaO. And now we are just going to go through and we take 24.8 grams. We would divide that by 100.01. And then we would multiply this by the 56.1 grams. Okay? So if we do this, we get a number of 13.9 grams of CaO. Okay? So this is now our theoretical yield. If we did this in the lab right now, we would take and weigh out 24.8 grams of the calcium carbonate. We would heat it up, and when we were done, after all the gas was released, we should have 13.9 grams of CaO. Now, of course, we could subtract these two numbers and figure out exactly how much CO2 was released as well. Okay, so this is now our theoretical yield. Now, once you have your theoretical yield, you can calculate how much you did, or how good of an experiment you did. Okay, so let's go ahead and go to the next slide. And so now we have a theoretical yield of 13.9. And let's just say we go ahead and do the experiment, and maybe we come out with more. Maybe we come out with less. Okay, so now we do the experiment, and it says we got 13.1 grams of calcium oxide in the experiment. This is what we did in the lab. Okay, and so it's asking us to calculate the percent yield when we had that 24.8 grams when it heated. Okay, so now what we did in lab, we had CaCO3. We had the 24.8 grams here. We went ahead and heated it, and we only got 13.1 grams. Okay, so right away you can obviously see that we had less than what we started with, but we want to know how far off we are, what percent we did. So percent yield calculation is really easy. All you have to do is divide. So percent yield is actual, it actually should be, over your theoretical yield. So now we just divide these two numbers. So our actual that we got in lab was 13.1 grams, and what we theoretically should have gotten was 13.9 grams. So you divide those, and we'll get a number that is 0.0421, I think, or something. And so then we times that number by 100 to make a percent, because you always have to do that. And so you move that over 2 times, and we would get 94.2%. So this is actually a very good percentage. Okay, so we might have lost a little bit, maybe during the heating step. We didn't get all of it out of the beaker or a crucible, whatever it may be. But anything in the 90s is a really good percent yield. Now, if we want to calculate percent air for this, we would take these two numbers and we would subtract them first. Then we would divide the error over the actual, and that would give us a percent error. And I can just subtract this. I know exactly how much error I had, and it would be 5.8. So you can actually just quickly look at a percent yield calculation and figure out your error. So they're very closely related. Percent yield is what you'll probably use in college the most. So there you go. That's your theoretical yield and how you relate that to stoichiometry. Have a good day.